We are solving 1.33 in Griffith Electrodynamics. This is the vector function. We will verify the divergence theorem or Gauss's theorem. So we have a cube, one corner at the origin. It's each side is 2 units. So we have 6 faces of the cube that we need to consider, for the right-hand side to evaluate the surface integrals. And then we will take the divergence and find the volume integral. Volume integral is easier. Let's do that first. Let's calculate the divergence of this function. Okay, so I will take the partial x derivative of the x component, xy, so it's going to bring me y, plus partial y of the second one, that's going to bring me 2z, partial z of the third one, that's going to bring me 3x. So this is the divergence. Now, d tau for Cartesian coordinates is dx, dy, dz. And in this case, the integration limits are 0 to 2 for each of the variables. So let's do it. Divergence of v in d tau over this volume would be, okay, so we're going to take one integral at a time. So dz 0 to 1 and dy 0 to 1. This is z equals 0 to y equals 0. And then x equals 0 to 1 dx of y plus 2z plus 3x. Okay, so let's do the first one. Z equals 0 to 1 dz, y equals 0 to 1 dy. This x part will be 3x squared over 2. The others act like constants, so y plus 2z x. So evaluated from 0 to 1. All right, if I replace all x's with 1, I'm going to get 3 over 2 here, y plus, so 3 over 2 plus y plus 2z. At 0, both of them will be 0. Okay. All right, so now do the y integral equals z equals 0 to 1 dz. And the y integral, there's a y here, and then 2z plus 3 over 2 will act like a constant. So I will have y squared over 2 plus 2z plus 3 over 2 y evaluated 0 to 1. Okay, so let's continue. Equals to z equals 0 to 1 dz. And I substitute 1 for all the y's. I'll get 1/2 here plus 2z plus 3/2, which is 2 plus 2z. So I can factor out a 2, z equals 0 to 1, 1 plus z dz. Okay, let's do the final integral to z plus z squared over 2, evaluated at 0 and 1. This is 1 plus 1/2, which is 3/2 multiplied by 2. I should get 3. So that's the left-hand side. Divergence of v d tau equals to 3. Now, we have 6 more integrals to take for each face of the cube. So let's do that now. So I have surfaces, faces parallel to xy plane, z plane, and xz plane. So one surface, say at the bottom on the xy plane, that can be characterized at z equals 0, and the top surface at z equals 2. Both of them are parallel to xy plane. So that's how I'm going to designate each face. So for each of them, if you take this top surface, for example, dA is pointing, again, by convention, all dAs are pointing out of the surface, out of the closed surface. So this is parallel to z, right? If it was at the bottom, it would be in the opposite direction. So I need to write these 6 integrals for each of these. So for example, this one will be to the right parallel to y, etc. So let's write those integrals out and set up the integrals before we evaluate them. Because when we just set up the integrals, we might see some of them canceling, okay, or simplifying. So if you evaluate all of them, then you might waste some time unnecessarily. So I'm going to do that first. Okay, so parallel to xy plane at z equals 0, that's the bottom surface. dA will be, or that bottom surface, in the negative z direction. So dx dy, because it's on the xy plane, parallel to xy plane, negative z hat. Okay, so that will make my v dot dA equals to, I need to just consider the z component, which is 3zx, right? 3zx dx dy, and with a negative sign. Now, I can immediately say this is 0 because this is at z equals 0. There's a z here, which is 0. So this is going to be 0. So I'm done. I don't even have to worry about integrating there. So parallel to xy plane, now at z equals 2. Well, that's very similar, just in the opposite direction, right? So dA is dx dy, positive z hat. So v dot dA also will be very similar, except this is positive. Now z is equal to 2, so I'm going to replace z with 2, x, 3 times 2 times x, dx dy. That's basically it. So it's 6x dx dy. So that's one integral I need to take. So if I set up that integral, x equals 0 to 2 on that surface, and then y equals also 0 to 2, dx dy, 6x. All right. So integral v dot dA equals to, for that surface. All right. I'm not going to evaluate it. I will just leave it as it is. For now, we will evaluate a little later. So now go to YZ plane. All right. YZ plane. So I can have 2 possible dAs at x equals 0. It's pointing in the negative direction. At x equals 2 in the positive x direction. So parallel to YZ plane at x equals 0, I have dA, dy, dz, negative x hat. So that's going to give me v dot dA equals to. Now, since it's x hat, I just look at the x component. That's xy. So I have minus xy dy dz. Okay. Now, this is parallel to yz plane at x equals 0. So x equals 0. So this is 0. So this is immediately 0. Okay. I don't have to worry about that. So the other one, parallel to yz plane at x equals 2. Now the opposite of this, obviously, dy dz now positive x hat. So v dot dA becomes the same thing with a positive, here, positive of this one. So it will be xy dy dz. Well, x equals 2, y varies from 0 to 1. So this is going to be 2y dy dz. Very similar to this one. So I'm going to write it as v dot dA equals to, now I have y 0 to 2 dy, z 0 to 2 dz, and then the rest is 2 times y. So I need to evaluate that, and I'll leave it for now. The last surface is x parallel to xz plane. Okay, parallel to xz plane can happen at y equals 0 and y equals 2. y equals 0, it's negative y direction. That's the dA direction. At y equals 0, so dA becomes dx dz negative y hat. So v dot dA becomes, now I need to look at the y component. Oh, I noticed a mistake. Maybe not. No, it's good. It's good. So I look at the y component, which is 2yz, right? So I have 2yz with a negative sign, dx dz. Well, this is xz plane at y equals 0. So this y is 0, so it's going to give me 0, right? Now, parallel to xz plane at y equals 2. Well, similar stories we are writing here. So we have dx dz, positive y hat, v dot dA becomes 2y, which is 2 z dx dz. So we have 4z dx dz. Okay, so v dot dA. So I have y equals 0 to 2 dx, z equals 0 to 2 dz, and then I have 4z here. Okay, so I have 3 integrals to evaluate. The others turn out to be 0. But look at the similarities between all these integrals. So if I pull out 6, so here I have 6 x 0 to 2 dx, y 0 to 2, so let me just change this, dy, x dx dy, right? So if you look at this one, it's also similar. It's like 2 y equals 0 to 2 y dy, z equals 0 to 2 dz. Look at these integrals. I mean, the variables, but the integrals look very similar. So this is the thing, you know, if you do it one at a time, you'll just spend the time for each of them. I mean, if you do this, this integral should be equal to this. It's just that 2, 6, you know, just add them. Here, the same thing, 0, you know, 4 times. You have y equals 0 to 2 dy. I made a, okay, x equals 0 to 2 dx. X equals 0 to 2 dx. I just made this mistake. Let's correct that. And then z equals 0 to 2 z dz, right? Again, the same thing. So 4 of them, 2 of them, 6 plus 6, 12. 12 of the same integral. So let's put them all together. So the entire surface integral will be surface integral v dot dA will be 12 of x 0 to 2 x dx, y 0 to 2 dy. Let's evaluate them. This is 12 times x squared over 2, evaluated at 0 and 2, times y evaluated at 0 to 2. Well, this is 6, 2 squared 4, 24, 24 times 2, 48. All right, this is 48. For the volume integral, I found 3. Well, I realized I made a mistake with the integration limits. Okay, I believe the surface integrals are correct, but the volume integral, I used wrong integration limits. Let's fix that. So integration limits had to be 0 to 2, not 0 to 1. So I need to just change all these. And it's going to create some changes, obviously, in the results of the integrals. So the first thing is, again, 2, this is going to be evaluated at 2. So I'm going to replace every 2, x here is by 2. Now 2 squared is 4, 4 over 2 is 2, this is 6. This is going to be 6. And there will be a 2 here, right, because of the x. Now, again, 0 to 2, 0 to 2. Let's look at that. So if I now evaluate the y integral, which is going to be, first you have 6 plus 4z, right? So it's going to be, this is going to be 6, this is going to be 4z, that's the constant part, and then 2y, so it's going to be 2y squared over 2, so these two cancel, and then evaluated 0 to 2. All right, let's move on. So this is y squared, 2 squared is 4 rather than 1/2 here, so I'm going to get 4. Okay, and then I have 4z plus 6 times y, so this entire thing will be 2 times 4z plus 6. Okay, so now what do we have here in total? 8z plus 12 plus 4. So it's 8z plus 16. So 8 factored z plus 2, right? So I have 2 plus z here, again, 0 to 2, and then factored out an 8. All right, let's do the last part. So it's going to be 2z plus z squared over 2. Evaluated 0 to 2. This factor is not 2, it's 8. Let's do this last part. 8, 2 times 2 plus 2 squared is 4 over 2. And that's 2. This is 4, 6. It's going to give you 48. So our method was correct. My integration limits were wrong, so I fixed them. Now it looks like we have verified the divergence theorem. This is 48. And the result of this, all these surface integrals is also 48. I hope you enjoyed the solution.